You're probably familiar with the impacts floods can have. Maybe you've even experienced one yourself. Even a moderate flood can have huge impacts on infrastructure, economies, and people's lives. Some floods are caused by hurricanes driving seawater on shore. Others are caused by intense precipitation overloading the natural capacity of rivers and groundwater, and still others are caused by seasonal melting of snow and ice. I study a very specific kind of flood called a glacier lake outburst flood. These extreme floods happen when a lot of water is released all at once when a dam breaks to release a lake, when water under a glacier suddenly escapes, or when a volcanic eruption melts a lot of ice at once. As you might imagine, these are really energetic events, and as such, they can be extremely destructive. This type of flood is relatively common today in the polar regions and high in the mountains, and is becoming more common as glaciers retreat. But if we go back further into the geologic past, we can find evidence of some really giant floods. The question I'm trying to answer is what these glacial lake outburst floods do to the surfaces they flow over, and how much they've changed topography in the past. To find out, I go to the deserts of eastern Washington to a weird landscape called the Channeled Scablands. This mysterious place is covered in canyons that were carved by outburst floods from glacial Lake Missoula, a lake that formed during previous ice ages when glaciers blocked the path of the Columbia River. Once the lake filled up to a certain level, the pressure on that ice dam would reach a critical point and the water would burst through, doing what water does in finding the quickest way downhill. Since the position of the glacier kept shifting around as climates changed, the flood route shifted around as well, creating this network of exposed bedrock where floodwaters stripped the glacial soil cover away. What I'm interested in here is what the canyons themselves can tell us about how much water these floods were composed of. There's a strong relationship between the intensity of a flood and the amount of rock it can remove for a given erosion mechanism. The Scablands is a great place to investigate this relationship because most of the rock exposed at the surface here is basalt, cooled from ancient lava flows, that has a very regular fracture pattern called columnar jointing. These cracks formed naturally as the rock was cooling along parallel heat gradients, and results in these blocks of similar shape and size. When the floods hit, some columns got plucked out in weak areas near faults and folds to form a waterfall. The waterfall grew and its position moved upstream as columns toppled right at the waterfall's edge, leaving a canyon behind. We have a few important limits on flood sizes here from the geologic evidence. First, there's the size of the columns and the eroded bedrock pieces. A bigger flood can erode bigger columns, and since the columns have such a simple geometry, we have a pretty good idea of what that relationship is. In other words, a flood has to be intense enough to move all the rock that we see was moved. Second, there's the maximum flood extent delineated by the soil-rock boundary. We know that floods can't extend past this boundary. Soil is really easy to move, and pretty much any amount of floodwater would have stripped it right away. Our computer models can simulate the Scablands floods, and we compare the stress and depth to these two limits to come up with a range of possible flood conditions. But if the floods were responsible for forming canyons, we need to take into account how the landscape looked at different stages of canyon formation if we want to know about conditions during a flood. That's where dating comes in handy. We collect samples of flood-transported boulders to take back to our lab and measure the length of time they've been sitting on the surface. Once a rock is eroded from its parent body and is deposited on the surface, it's exposed to cosmic rays, which cause slight changes to the isotope ratios in the rock at a predictable rate. Our lab is equipped to measure beryllium-10, the result of oxygen found in quartz, losing a couple of subatomic particles. We remove a piece from the top of that boulder, crush it up, separate the quartz crystals using a big magnet and a lot of acid, and pull out the beryllium using a couple different chemical processes. Then, we send it off to the fancy mass spectrometer to measure how much beryllium-10 we have and convert that into an age. We use the age of these flood-transported boulders as a proxy or substitute for how long it's been since a surface was last impacted by floods. A big flood would sweep away any boulders left in its path by the previous flood, but as the canyon grows and deepens, it abandons some surfaces and the boulders sitting there are preserved. These dates, combined with the field evidence of surface change and our computer simulations, are allowing us to reconstruct conditions during a flood for lots of different times in this landscape's history. Our work is helping us understand how flooding has changed this landscape, as well as how changing landscapes have affected flood conditions. The channeled scablands is famous among geologists for preserving evidence of megafloods and showing us how much erosion they're capable of causing. But they're not the only place where extreme floods have dramatically shaped the landscape. Lake outburst floods have been documented on a smaller scale in Arctic regions, forming features like these canyons in Norway. Humans build dams for hydropower and flood control, which could cause widespread damage if they were to fail. And some research has suggested that the Mississippi Valley, the English Channel, and even some canyons on Mars were initially formed by extreme floods even bigger than the ones in the scablands. The idea that extreme events are more important than slow and steady processes in shaping the landscape in certain places is relatively new in the field of geology, where most of the time we think about long, slow, and old things. The research I'm doing on the Missoula megafloods will help us understand the physical processes by which extreme floods carve canyons and change topography, and how important megafloods would have been in shaping landscapes around the world.